Welcome all. In this lecture, we will discuss about transfer function of mechanical systems. So first we can consider translational mechanical system. So translational means it is linear motion, linear mechanical system. So while considering the modeling of translational mechanical system, you have to consider these three mechanical elements, mainly these three elements: mass, spring, dashboard or damper. So by these three elements, we can model all the linear mechanical systems. So first we can consider the mass. So let us consider the element mass with having mass m, and we are applying a force F on it. So it will cause a displacement x. X is the displacement if we are applying the force F m on the mass m. So by Newton's law, this mass will oppose the applied force by a equal and opposite force Fm, where Fm is equal to m into a, where m is the mass and a is the acceleration of the element. So a and displacement x are related as a is the acceleration and x is the displacement. A is equal d square x by dt square. So it becomes m into d square x by dt square. So again this opposing force Fm and applied force F are equal. So F equal to Fm, which is equal to m into d square x by dt square. So this is the equation for mass, m into d square x by dt square. Next is spring. So consider the element spring having a spring constant k. If you are applying the a force F on it, it will cause a displacement, and the spring will oppose the applied force by a equivalent and opposite force Fk. So Fk is proportional to x, where Fk equal to k into x, where k is the spring constant. So again Fk and F are equal, applied force and opposing force are equal, so F equal to Fk is equal to k into x. So kx is the equation for spring element, where k is the spring constant, x is the displacement. Next is dashboard. So dashboard or damper, this will represent the frictional element or frictional force. So if B is the frictional coefficient, and F is the applied force, x is the displacement, and the dashboard will oppose the applied force by equivalent force Fb. So Fb is proportional to v. V is the velocity. Again velocity and x are related such that v is equal to dx by dt, differential of displacement, and b is the coefficient of proportionality, so Fb equal to b into dx by dt. So again F equal to Fb, so it becomes b into dx by dt. So for dashboard the equation is b into dx by dt. So the three elements are mass, spring and dashboard. For mass the equation is m d square x by dt square. For spring the equation is kx, and dashboard it is b into dx by dt. Dashboard is also a frictional representation, okay, frictional force representation. So we can also use for frictional force also, frictional. So next we can discuss how we can find the transfer function of translational mechanical system. So consider this system, it is having a mass m, and it is experiencing a frictional force and spring constant. Okay, so dashboard B and spring K, having a spring constant K. The mass is having a mass m, so applied force is F and the displacement is x. So here F is the input, we are applying the force, so it is the input, and x is the output, displacement due to this input. So F is the input and x is the output. So transfer function means x of s by f of s, output by input. So first, in order to find the force balance equation, we have to draw the mass free body diagram of this m. So free body diagram of m, we have to first mark the applied force. So applied forces are only F. Okay, F is applied on the mass, and the opposing force are due to this m, this b and this k. So this is fixed. The mass m is moving by the element by the displacement x. So the mass, the opposing force by the mass is Fm, which is equal to m d square x by dt square, and by the dashboard b is Fb b dx by dt, and by the spring constant is kx, so Fk equal to kx. So these are the forces, applied force in this direction, and the opposing forces are opposing to the F. So we can write the force balance equation as here only F and here these three forces, m d square x by dt square, b dx by dt kx. Then for finding transfer function we can apply the Laplace transform without initial condition. Since it is transfer function, no initial condition can be found. So the Laplace of f is f of s, x is x of s. So d square x by dt square is s square x of s, dx by dt become s into x of s, x become x of s. So again f of s equal to, we can take x of s outside, and transfer function is output by input. So f is the input and x is the output. So x of s by f of s, so become 1 by ms square plus bs plus k. So this is the transfer function. So here the system is very simple, only one mass. So if there are number of masses, we have to draw the free body diagram of number of masses m1, m2, m3, and we have to write the force balance equation for each masses. For example, consider this diagram, mechanical system. So there are two masses m1, m2, and f of t is the input, applied force. It is applying on m1. So the displacement of two masses m1 is x1 and m2 is x2. We are taking the x2 as the output. So the transfer function is output by input x2 of s by f of s. So we have to draw the free body diagram of both two masses m1 and m2. So first we can write free body diagram of m1. So the applied force is f of t. So f of t this side, and the opposing forces will be due to this mass m1, due to this b1, and due to this k1. Okay, so due to this m1 the displacement is x1. So m1 d square x1 by dt square, first force. Next one is this k1. So if you are looking this k1 and b1, k1 is attached to this m1 and m2, so it will be experiencing displacement x1 and x2. So now we have to consider x1 and x2. The equation is k into x, force equation is k into x for spring, but here x1 and x2 are there on each side. Now we are considering this m1, so we have to take first x1, then x1 minus x2. So the equation is k1 into x1 minus x2. First we are considering m1, so we have to first take x1, then minus x2. It is in between these two, so we have to consider both x1 and x2. Again this b1, so the equation is b into d by dt of x. Again b is attached to m1 and m2, so we have to consider x1 and x2. So first we have to consider x1 because we are considering now m1. So b1 divided by dt of x1 minus x2. This by minus this, so x1 minus x2. So this is the free body diagram of m1. Next, free body diagram of m2. So for m2 there is no applied force, so there is no force in this side, only opposing force will be there. Opposing force are due to this b1, k1, this m2 and k2, b2. So for first, for the mass itself, mass of itself, so it is m2 into dx2 square by dt square. Okay, we are considering this mass, so x2. Again this term b1, so b1 into we have to take both the displacements x2 and x1, but we are now taking m2, the free body diagram of m2, so we have to take x2 first, so x2 minus x1. Then again k1, so k1 also it is attached to two bodies, two masses, so we have to take x2 and x1. First we are considering m2 here now, so x2 minus x1, k1 into x2 minus x1. Then this b2, so b2 is only attached to m2 only, it is reference here, it is fixed here. So b2 into dx2 by dt only. Then k2 also attached to only m2 only, this side is fixed, so k2 into x2, kx. So now we got the free body diagram of these two, so we can write the equations, force balance equation of both. So first we can write the force balance equation of m1, so it become this side f of t and this side these three forces, m1 d square x1 by dt square, k1 into x1 minus x2, b1 divided dt of k x1 minus x2. Then we can take the Laplace without initial condition. So f of t become f of s, d square x1 by dt square, s square into x1 of s. Here k1 x1 minus x2, so x1 of s minus x2 of s. Here d by dt of x1, so s x1 of s, d by dt of x2, s into x2 of s. So we can take x1 of s. So x1 of s will be equal to f of s minus b1s plus k1 into x2 of s. Here this k1 x1 of s here, b1 s1 of x, x2 of x here. Okay. So divided by m1 s2 s square plus b1 s plus k1. Now we can take the force balance equation of m2. So let this equation 1 force balance equation of m2. There is no force applied, so 0 here and 1 2 3 4 5 forces here. So it will be like this, and we can take the Laplace. So it become m2 s square x2 of s b1 s into x2 of s minus x into x1 of s k into x2 of s minus x1 of s b2 s x2 of s k2 x2 of s. So we have these equations. So now we can rearrange this. So here we can take the x2 of s terms first. So m2 s square, here b1 s, b2 s, then k1 k2. So m2 s square, b1 plus b2 s, k1 plus k2 for x2 of s, and this is minus b1 s x1 of s. So when we are coming to this side, become b1 s plus k1 x1 of s. So now we can substitute for x1 of s from equation 1. So this term become f of s minus b1s plus k1 x2 of s by m1s square plus b1s plus k1. Now we can multiply this. So this f of s, here b1s plus k1, here the denominator, here b1s plus k1 whole square. So again we can take x2 of s this side. So it become, we can multiply this or we can take this term to this side. So plus b1s plus k1 square x2 of s by m1s square plus b1s plus k1, x2 of s this side and f of s this side. We have to find x2 of s by f of s. Again we can multiply this and add this. So we can take it as, this will be cancelled. So this into here. So m1 s square plus b1s plus k1 into this term into x2 of s plus b1s plus k1 whole square x2 of s equal to this side b1s plus k1 f of s. Denominator will be cancelled. Then we can write x2 of s by f of s as, here b1s plus k1, here this whole term m1s square plus b1s plus k1 into m2s square plus b1 plus b2s plus k1 plus k2 plus b1s plus k1 whole square. So by this we can find the transfer function. Now another example, we can also have the frictional coefficient here also. If this, we have to consider the frictional coefficient here if it is given by this plane and this body m1 and m2, b11 and b22 is given. So we have to take b11 dx1 by dt for this, and for m2 b22 dx2 by dt. So we can write the free body diagram. For m1 applied force is f of t, and there will be due to m1 d as previous m1 d square x1 by dt square, then k x1 k1 x1 minus x2 b1 d by dt of x1 minus x2. Additional to that, there will be this term b11 dx1 by dt, frictional force. We have to take the friction also. So that we can take this dashport, because dashport is a presentation of friction. Similarly for m2 also, terms will be first due to m2 d square x2 by dt square, then b2 this is b1, okay, b1 into x2 minus x1, then k1 into x2 minus x1, then addition to that there will be b22 dx2. We have to consider this also. Okay, the thing is we have to consider this also, and now we can write the force balance equation, and we can solve by applying Laplace. So the thing is, the example shows that we can also take the frictional coefficient also as b11 dx1 by dt, here b2 to dx2 by dt. Okay, with this we can wind up the session. Thank you.